Hello everyone, I'm Kevin from Team 21229 Quality Control. We were the 2023 First Tech Challenge World Championship Winning Alliance first pick and the Innovate Award winner in the 2023 and 2024 World Championships. Today, I would like to share some of our experiences on how to optimize robot design. During the Centerstage season, the improved robot design greatly enhanced our robot's performance. I will walk through improvements to our intake and transfer, Mosaic fixer, drone launcher, and hanging mechanism. During the Centerstage season, we built 2 robots. When I present about the improvements to each subsystem, I'll often reference what was on the V1 robot and explain how we optimized it in the V2 robot. To start off, here's a 2+A auto video that demonstrates our robot's performance. It is one of the few robots that can perform a 2+A without extendos. Without optimizing the robot design, our robot could not achieve such a good performance. Therefore, I would like to share how we improved our robot design throughout the Centerstage season. When optimizing robot design, it is very important to pay attention to many small details. Small issues or rarely occurring inconsistencies can affect the robot's reliability, especially in auto. An example of this is how we improved our surgical tubing inserts for our intake. While it may seem like a small change, it helped prevent the intake from unexpectedly breaking and losing the surgical tubing rollers. As shown in the figure on the left, in our first version, we used a zip tie to secure the surgical tubing. This required one part of the insert to be small enough for the zip tie to grasp the tubing tightly, which made the 3D printed piece weak and prone to breaking. Additionally, it was very difficult to install surgical tubing because of the large, round tip. In our improved version, we made the end of the insert significantly smaller to make it much easier to insert surgical tubing. We gradually increased the diameter of the insert, then reduced it to secure the surgical tubing. Our new design allowed the surgical tubing to be secured without a zip tie, while also being thicker and more structurally sound. Throughout the season, we did not encounter any issues with this new insert design. No breakage and no surgical tubing falling off. This example goes to show how changes in the design of a small part can significantly optimize its performance. Now, I will walk through an example of how we optimize the performance of our intake and transfer system. During the season, we learned that an effective intake and transfer must maintain complete control over the game element at all times. Otherwise, the game elements may move in unexpected directions, get stuck, or escape from the intake. To ensure this doesn't happen, the game element must remain in contact with each of the intake rollers or ramp at all times, which can be verified by testing the intake manually. At the beginning of the season, we encountered issues where the pixel would pop or fly off the transfer ramp. To address this, we added 3D printed roofs and covers along our transfer ramp, which you can see in orange over here, to prevent pixels from moving in undesirable directions. For example, at the end of the ramp, we installed a roof which was angled smoothly to gradually guide the pixel to a more horizontal position when entering the deposit box. We found that it was easy to control the pixel on a flat surface. However, when the pixel needed to change directions, it became more difficult. If there isn't enough space, the pixel may get stuck at turnaround points. Otherwise, if there is too much space, the pixel can fly out or multiple pixels can become jammed. To solve this problem, we added a gecko wheel as a soft roof near the turnaround point where the pixel changes angles within the transfer system. You can see this right here and right here. This setup prevents the pixel from getting stuck and also guides it along the ramp. In this picture, the pixel can slightly compress the wheel when changing angles and moving up. Sometimes, multiple pixels would get jammed near the top of the intake, and reversing the intake couldn't free them. The pixels would remain stuck for the rest of the match. We discovered that intake jams near the end of the ramp were extremely difficult to fix, so we added a small blocker in the middle of the ramp to prevent multiple pixels from getting stuck at the top of the transfer ramp. This video demonstrates how our intake and transfer handles possible jams. In our V1 robot's transfer, due to how our outtake worked, it had enough space to have more than 2 pixels clog up in the outtake. You can see that our 3D printed scoring mechanism was tilted slightly up, basically due to its design and how it worked, so it allowed more pixels to get in and get stuck. If multiple pixels got into the robot, they could really easily get stuck there. Since our intake transfer ramp angle was really steep, as shown by the green arrow, reversing the intake and getting rid of stuck pixels was much harder. So we had to be really careful to not intake more than 3 pixels. In our V2 robot's transfer, our outtake was modified so it only had space for 2 pixels. As you can see, this claw mechanism over here covers the whole deposit box really well, so a 3rd pixel would be physically unable to enter the outtake box no matter how powerfully the intake rollers were pushing it. Therefore, the deposit box would always contain exactly 2 pixels regardless of how many pixels entered the intake. A shallow intake transfer ramp angle, as shown by this green arrow, means that the 3rd pixel can more easily be spit out of the intake. This design and the blocker I mentioned in the previous slide helps prevent pixels from getting permanently stuck inside the intake ramp. As a result of these improvements, we were not worried at all if the robot accidentally intakes many pixels. We would always be able to get rid of any extra pixels in the robot. This was crucial in helping us get a better auto. For our first robot, we designed what we called 3D printed flappers, each controlled by a servo to smack the bottom pixel out of the intake and into the stack. Out of the stack and into the intake. This allowed us to achieve a 2+4 auto. You can see this design in action here. However, this design was not the most consistent because it relied on the robot and pixels orientations to succeed. As shown here, if the pixel orientation was slightly rotated, it could get stuck and the pixel wouldn't be able to enter the intake. So, for a V2 bot, we designed a deployable intake. It is wider and can intake pixels at any height on the stack. You can see this right here. You can see that the intake can just lower to reach another pixel on the stack. Even if the robot was off by a couple of inches, it could still pick up from the stack very quickly. Additionally, this new intake allowed us to pick up 2 pixels stacked on top of each other during teleop. We also use sensors to improve the accuracy of our intake and transfer system. We installed 2 pairs of beam brake sensors in our deposit bucket. You can see one of them right here. In each pair, one sensor emits an IR light to the other sensor, the receiver. The receiver detects that the IR If the receiver detects that the IR beam is broken, the robot knows it has a pixel. This setup helps the robot reliably detect the number of pixels it has. For instance, during auto, the intake automatically reverses after the robot collected 2 pixels, preventing the possession of 3 pixels and avoiding penalties. If the beam break sensors detect fewer than 2 pixels in the outtake, the deployable intake lowers to reach another pixel on the stack. We connected the beam break sensor signals to the LED lights. A blue light indicates 1 pixel and a green light indicates 2 pixels. This feature was very useful for us during teleop, since the drivers cannot easily see how many pixels they have in the robot. Instead, they can just look at the color of the LED lights to determine if they need to intake another pixel or if they need to score. Now I'll talk about our backdoor mechanism that was added to the deposit box. We designed a rotating door at the back of the box to release stuck or unwanted pixels from the robot, preventing pixel possession penalties. This also gave us the option to score pixels on the backstage if the robot broke and we were unable to score on the backdrop. During auto, we always open the feed door after every cycle to eliminate any pixels that couldn't be grabbed by the outtake. As a result, the robot would always score something, even if the outtake malfunctioned. Overall, this design provided the robot with more flexibility and mitigated the impact of unexpected failures. In general, these failsafes can optimize robot performance. Next, these 3 videos show how the optimizations I mentioned previously helped us a lot in auto. Having a wider intake meant that the robot had a larger error margin when gathering pixels, and you can see that it wasn't completely aligned with the pixel, but it could still successfully pick it up. Having beam break sensors allowed the robot to automatically get rid of any extra pixels and prevent penalties. You can see that the robot was able to detect, showing that it had a green LED light. It was able to detect that it had enough pixels, and it was able to spit the extra ones out. Finally, if the beam break sensors detected fewer pixels, the intake will lower and the robot will move to get another pixel. You can see that the LED lights turned blue, meaning that the robot only had 1 pixel. So it would try to get another pixel. You can see that the LED light suddenly turned green, meaning that the robot recognized it had enough pixels to score. So it moved away and got rid of any extra pixels in the robot. Once again, the LED light turned blue, denoting that the robot doesn't have enough pixels. Eventually, after enough time, it detects that it can't get another pixel and moves to the side to get the last one. Now I'll talk about our robot's Mosaic fixer. Often, pixels wouldn't be scored in the best location, preventing possible mosaics. Since mosaics were worth many points, we decided to have a mechanism to fix broken mosaics. Initially, we tried using our outtake claw to relocate pixels on the backdrop and fix mosaics, but it was hard to do so. It was very difficult to see whether the tip of the claw was really grabbing the pixel correctly. We instead added a separate mechanism to fix mosaics, as you can see here. using a servo that rotated a beam that could go inside the pixel's hole. Now it's much easier to see what's going on. Here's a video that demonstrates this mechanism. Though initially we used some flexible surgical tubing, later we decided that to use a hard beam, as that worked better for us. Now I'll present some improvements to our drone launcher. This was our first drone launcher design, powered by rubber bands and made with GoBuilda channels. It was easier to build, but sometimes the drone wouldn't fly out of the field or it would fly too far. Because it only used GoBuilda, it occupied a slightly larger space and had a wide launching channel. So the drone's angle in the channel could vary. As you can see, the red line here could be at many different angles between the blue channels. So the drones could be launched in different ways, causing inconsistency. Additionally, the rubber bands only accelerated the plane at one point, shown here. This meant that the plane could be shot in different ways, causing more unreliability. This also caused the back of the paper plane to wear out over time. So, in our next iteration, we made sure that the plane was launched at a consistent position. To do so, we used custom 3D printed parts to minimize the width of the slot the plane was put in. You can see the design here. We used surgical tubing to power the drone launcher. However, instead of making it contact with the plane, the surgical tubing was tied to a 3D printed accelerator, which you can see here, that the drone was put in. This way, the accelerator would be moving the plane at an entire surface, making the flight more reliable. Also, after shooting many times, the back of the plane wouldn't get deformed from the surgical tubing. This picture here shows how we mounted our surgical tubing. We used 3D printed slot caps, which you can see here, which we put over the surgical tubing to secure it easily. We also designed our drone launcher to be more easily and quickly fine-tuned. We made the angle of the drone launcher adjustable, using a slot to test different flight trajectories. You see the big arc here allows the drone launcher to be built in many different angles. When preparing for the state championships and doing driver practice by ourselves, the drone always gave us a consistent 20 points. But when scrimmaging with other teams, the drone failed and didn't get close to flying out of the field. After each practice match with other teams, we tested our drone, but it succeeded every time. We initially thought that our robot would sometimes get stuck on the center door, causing the drone to move and get damaged. So we modified our drone launcher to solve that, but in our next scrimmage, our drone still failed. We were very confused why our drone succeeded when testing on our own, but failed in the presence of other robots. To investigate, we stopped driving the robot during endgame and observed what happened to the plane. We discovered that the plane had moved out of the trigger during teleop, causing its flight to be completely messed up. Most likely when our robot collided with other robots, the drone would slide out of the 3D printed trigger. To solve this, we improved our 3D printed cover to block the plane from sliding out of the drone launcher. And with that, our drone launcher continued to be consistent at the state championships. Here's a video that demonstrates our drone launcher. At the World Championships, we again learned to anticipate robot collisions more and keep important subsystems further inside the robot. Our drone launcher in our V2 robot was mounted at the very front of the robot, and though we added a beam to protect it from collisions, it could still get affected. In our first qualifier match at Worlds, the drone launcher was hit and its angle changed, causing the drone to fail. That night, we designed and 3D printed a guard, which is shown in this image, to protect our launcher. And later, it didn't get affected from robot collisions anymore. Now I'll present our improvements to our hanging mechanism. We initially decided on using a lead screw to extend our hanging mechanism. This is because once the lead screw extends, it can't easily retract, even when the motor is not powering it. This means that hanging the robot wouldn't easily burn the motor and it would be very reliable. However, to pass under the center door, the robot had to be under 12 inches. Unlike slides, lead screws don't have multiple stages, so in order to reach the rigging height of 24 inches, a lead screw would have to be over 12 inches, meaning that the robot wouldn't easily pass through the center door. To solve this, we use string to passively rotate the end of the hanging mechanism, and you can see this placed here. When the lead screw extended, it would make the string pull on the hanging hook, eventually making it upright. Once the lead screw extended, the string would not allow the hanging hook to rotate back towards the ground. To prevent the strings from going to unwanted positions and getting stuck on something, we secured it between a dual block, as seen here. One potential problem was that each field would be different, and a difference in the rigging height could affect whether the hanging hook could secure itself on the rigging. So we added chamfers, which you can see in this diagonal edge here, that could increase the error margin when the robot was aligning to the rigging. You can see in this picture that even though the rigging is slightly a bit higher than the hook, the chamfers can guide it so the hook can still get on. Unfortunately, when hanging the robot, it could take several seconds before it would be off the ground. One reason was that the hanging hook was to the side of the robot, and the lead screw would need to retract a lot before both sides of the robot would be off the ground. You can see in earlier versions of a robot, it's barely leaving the ground because it's so slanted in the air. For our States robot, we designed our hanging hook to be wider. Therefore, the robot could be more parallel to the ground when hanging, and the lead screw would retract less to get the robot off the ground, meaning that the hanging could be completed quicker and more reliably. However, since lead screws sacrifice speed for high torque, we still wanted a way to hang more quickly to maximize our robot's potential. To speed up our endgame, we decided to use the faster vertical slides to hang. Initially, like most teams who use their vertical slides to hang, we put the hanging hook at the end of our slides. However, this caused a large force along the vertical slides, and our robot would not be parallel to the ground when hanging. As you can see here, it's very slanted. The slides would have to almost fully retract before the front of the robot finally left the ground. And at the end of the match, the robot would take a big fall when the slide motors lost power. This caused some of the 3D printed parts of the robot to break. So in our next hanging hook, we moved it more towards the center of mass, so the robot would be more parallel to the ground when suspending into the air. To do so, we created a lot of holes on our hanging hook to quickly adjust its position to get closest to the robot's center of mass. Our robot would take a very small fall when the match was over and nothing broke again after hanging. We also designed a wide opening for the hanging hook to allow more air margin. If the hook's position was slightly above or below, it would still be able to get on the rigging. Finally, we added foam on the hook to prevent the robot from swinging into the air, speeding the mechanism up. Here you can see how this works. That's the end of my presentation. I hope you learned something, and please let us know if you have any questions through our Gmail. Have a great next season.